And we're back. Hi again. This is the last part of the 3 lectures presenting the steps for sizing a battery for an electric vehicle. Previously we have looked at energy and power requirements separately. Now we will combine the energy and power requirements. This diagram shows the battery energy content on the horizontal axis and the battery power on the vertical axis. We can draw the maximum discharge power as an upper limit for the battery power. As we found in an earlier presentation, it's 102 kilowatts. And the maximum charge power at regeneration is 20 kilowatt. This means that the battery must be able to deliver any power within this range. Now we add the required energy as the upper limit for the required battery operating range. And the minimum limit is when the battery energy is 0. So this is the required energy. Since the battery operating point has to stay within all these limits, the operating range will have these borders, represented by this area. Now we will compare the required operating region with the operating region which is allowed to find the size of the battery. First we size the battery to have 32 kilowatt-hour capacity as required to meet the 300 kilometer range requirement. Then the battery will have this allowed operating region. We can see that the required maximum power is higher than the highest battery power. If the same type of battery cells are used, it's not possible to increase the power alone. The battery power and energy will scale together along this line, determined by the maximum current of 3C. So to meet the highest power, the energy has to be increased to this level, which is 34 kilowatt hours. The 34 kilowatt hour version of the battery will have this allowed operating region. The battery can now meet the peak power requirement, but only when it's fully charged. At lower state of charge, there is a lack of battery power in this part of the operating region. If we shall meet the peak power requirement also at lower state of charge, the battery will have to be even bigger. 40 kilowatt hour seems to meet the power demand, except at very low state of charge. So, if we just select the 40 kilowatt hour battery, what performance can we expect? First, we just move the operating region up to use the full energy capacity of the battery. This is only done to make it easier to show which advantages the bigger battery has. This extra energy leads to a longer driving range. The 40 kilowatt hour will be sufficient for 375 kilometer instead of the required 300 kilometer. This high charging power means that a high power regeneration is also possible. This extra power allows higher battery power than required at high battery state of charge. Note that the electric drive system might not need to be resized in order to make use of this extra power, so this extra battery discharge power doesn't necessarily become useful. Despite the bigger battery, it is still not possible to provide the required 96 kilowatt power at low state of charge, but it is first after having driven more than the required 300 kilometer that there will be a reduced vehicle performance. Most of the driving will still work exactly as normal, but in the most power-demanding situations, the performance will be reduced. The driver will first notice a gradual reduction of the maximum high-speed acceleration of the vehicle, since that is the most power-demanding driving situation. At very low state of charge, like under 5%, the vehicle will have a much reduced power, which will be noticeable also in less demanding situations. For this vehicle, the power requirements constitute the sizing criteria for this type of energy-optimized battery. This means that the battery cannot be made smaller even if the required driving range is lowered. Only if the power demands are reduced, the battery can be made smaller. Since power is the limiting factor, we might like to investigate the required size of a power-optimized battery. This battery type has a maximum current of 5C, So if we select a battery of just 32 kWh, we get this possible operating region, which shows that a 32 kWh battery is sufficient. This battery will be able to supply a much higher power than required. It is also capable of high power regenerative braking. But just like for the energy battery, it also has a limited power at low state of charge. So, we have a choice to make. We compare some key factors for the energy optimized battery and the power optimized battery. The battery cost is most likely lower for the energy optimized battery. It has a 25% higher energy content, but the battery cells are likely to cost less, such that the total cost of investment is lower compared to the power optimized battery. The driving range with the energy optimized battery is 375 km, while the power optimized battery has just a 300 km range. 300 km is according to requirement, but of course 375 km is better for the user. Battery power is one of the advantages of the power optimized battery, but the increased battery power can't be used unless the drive system is resized. All in all, most things speak for the energy optimized battery for this car. The longer driving range might have a high value for the owner, and so does a low cost for the battery. Other advantages of power optimized batteries, like capacity for many charging cycles, have limited value for a normal car. However, for a business application like for a taxi, the possibility of fast charging might be of high value. It's possible, even likely, that a car manufacturer would consider lowering the acceleration requirement such that the battery power may be reduced in order to be able to reduce the battery size and thereby the cost. So, let's conclude both battery sizing and the size of the electric powertrain for our example battery electric vehicle. To meet the vehicle requirements, the gear ratios shall be 7.1. The electric machine shall have 212 Nm of torque, a maximum speed of 12,500 RPM, and a maximum mechanical power of 95 kW. A 40 kWh battery will supply the power, and it's built from energy optimized battery cells. The range is 375 km, which is 25% more than required. This requirement overshoot stems from the high acceleration requirement and the fact that it's favorable cost-wise to oversize an energy optimized battery rather than selecting a power optimized battery. In this lecture, you have learned a method to size batteries to meet both power and energy requirements. We also concluded the sizing of a powertrain for a battery electric vehicle. So now you know the main steps involved in sizing a battery electric powertrain and its battery to meet a set of vehicle requirements. Now click next to practice sizing of a battery for an electric vehicle.